On the night of January 26, 1700, a wave hit the eastern coast of Japan. It flooded rice fields, damaged buildings, and was carefully recorded by local officials, as Japanese coastal communities had done for tsunamis many times before. But this one was strange. There had been no earthquake felt beforehand. No warning shake, no known local cause. For centuries, Japanese records simply listed it as unexplained. Historians and seismologists later gave it a name, an orphan tsunami, a wave with no local parent earthquake to explain it. The mystery sat quietly in old records for nearly 300 years. Then, in the 1980s and 90s, a very different kind of researcher started looking at a very different kind of evidence. On the opposite side of the Pacific Ocean, along the coast of Washington and Oregon. Indigenous oral histories, passed down for generations among coastal nations, described a night when the ground shook violently and the sea rose without warning. Geologists studying the coastline found something that matched. Entire forests of cedar trees, killed instantly when the land they stood on dropped several feet during a massive earthquake, then stayed drowned in salt water ever since. Locals call them ghost forests, and they still stand today. Tree ring dating pinned the tree's death to the same year, 1700. And the timing lined up precisely with the mysterious wave in Japan. There was no coincidence. A massive earthquake, one that left no felt tremor in Japan strong enough to explain the wave on its own, had occurred along a fault stretching hundreds of kilometers off the coast of North America. The wave crossed the entire Pacific Ocean in about 10 hours and reached Japan with enough force to be written down by careful record keepers who had no idea what caused it. This is the story of how an orphan tsunami in Japan and a forest of dead trees in America solved one of the biggest gaps in North American seismic history, and what it reveals about a fault that has stayed quiet ever since. To understand why this fault produced a wave big enough to cross the entire Pacific Ocean, we need to understand what kind of fault it actually is. The Cascadia subduction zone is what's called a megathrust fault, the same category responsible for the largest earthquakes ever recorded, including the 2011 Tohoku earthquake in Japan and the 2004 Indian Ocean earthquake. These faults form where one tectonic plate slides beneath another. Off the Pacific Northwest coast, the Juan de Fuca plate is slowly diving underneath the North American plate at a rate of a few centimeters per year, roughly the speed your fingernails grow. Most of the time, that boundary doesn't slide smoothly, it locks. Friction holds the two plates together while the deeper parts of the plate keep moving, bending the upper plate like a loaded spring. That bending is invisible day to day. It happens over decades, even centuries, storing enormous amounts of energy. In 1700, that spring released all at once. Modern estimates place the magnitude at approximately 9.0, based on the height and reach of the tsunami recorded in Japan, cross-referenced with the amount of coastal subsidence found in the ghost forests. A rupture that size doesn't just shake the ground. It can drop entire sections of coastline by a meter or more in seconds, which is exactly what killed those cedar trees instantly. What makes megathrust faults especially dangerous isn't just the shaking, it's the displacement of the seafloor itself. When a fault that size ruptures underwater, it doesn't just move rock. It moves an enormous volume of ocean water vertically, all at once. That's what generates a trans-Pacific tsunami, capable of reaching a coastline 8,000 kilometers away, with enough energy to still be dangerous. Since 1700, this fault has been locked again, quietly bending, quietly storing stress, which is exactly why modern researchers monitor it as closely as they do. Next, we'll look at how scientists actually reconstructed the exact timing and scale of this event, hour by hour, using nothing but tree rings and a single Japanese village's tax records. Here's where this story becomes a genuine piece of scientific detective work. Reconstructing the exact timing of the 1700 earthquake required two completely independent lines of evidence. gathered nearly 300 years apart, on opposite sides of an ocean. The first came from Japan. Local magistrates in coastal villages were required to report unusual events, including flooding, to regional authorities, partly for tax and land use reasons. These records included specific details: which fields flooded, how high the water rose, and critically, the date. Because Japan used a well-documented calendar system at the time, researchers could convert these records into a precise Gregorian date, January 27, 1700 local time, meaning the wave struck late in the evening of January 26th on the North American side, accounting for the time difference. The second line of evidence came from tree ring dating, a method called dendrochronology. When the Cascadia Fault ruptured, entire stands of red cedar trees along the coast were killed almost instantly by sudden submersion in salt water. Trees add one growth ring per year, and the pattern of ring widths acts like a fingerprint, shaped by each year's specific growing conditions. By matching the ring pattern of the dead trees to a continuous record from living old-growth cedars nearby, researchers could identify the exact final year those trees were alive, 1700. Some samples were precise enough to suggest the trees died before that year's growth season began, consistent with an event in the winter. When both timelines were placed side by side, they matched within hours. A tsunami recorded in Japan on the night of January 26th to 27th, and a forest of trees in North America that stopped growing at the very end of 1699, going into 1700. This wasn't a coincidence found by luck. It was built from decades of patient, cross-disciplinary work, historians translating centuries-old Japanese records, and geologists counting tree rings one by one under a microscope. The two independent data sets confirmed each other in a way that left very little room for doubt. This kind of reconstruction is now used as a model for studying other historical earthquakes worldwide, proving that even without seismographs, careful science can date a 300-year-old earthquake to within a matter of hours. Next, we'll look at what this discovery changed about how the Pacific Northwest prepares for the future, and what still isn't fully resolved. The discovery of the 1700 earthquake changed something fundamental about how the Pacific Northwest understands its own risk. Before this research came together in the 1980s and 90s, Cascadia was largely treated as a low-risk zone. There was no felt earthquake in the historical record strong enough to suggest a fault capable of a magnitude 9 rupture. Building codes, infrastructure planning, and public awareness all reflected that assumption. Once the 1700 event was confirmed, that assumption had to be rewritten. Oregon, Washington, and British Columbia updated seismic building codes to account for megathrust level shaking. Coastal communities began developing tsunami evacuation routes and vertical evacuation towers, structures specifically built for people to reach safety when there isn't time to run far. Public education campaigns started teaching a simple, memorable rule that's now taught in coastal schools throughout the region. If the ground shakes for more than 20 seconds near the coast, don't wait for an official alert. Move to high ground immediately. But not everything about this fault is resolved. Scientists still don't know exactly how the roughly 1,000-kilometer length of the Cascadia zone ruptures, whether it breaks in one enormous event like 1700, or sometimes in a series of smaller, segmented ruptures. Sediment records suggest both patterns may have happened at different points over the last several thousand years. That uncertainty directly affects how strong the shaking could be in any future event, and it's an active area of ongoing research. What this case really demonstrates is something worth sitting with. An earthquake with no historical record in an entire country can still be reconstructed, understood, and prepared for, using tree rings, old tax ledgers, and patient cross-continental collaboration between researchers who, in most cases, never met each other while doing the work. That's what separates real seismology from speculation. Not certainty about when the next one comes, but a genuine, evidence-based understanding of what happened before and what's still being measured today. If you want to see how the 4 seismic gaps we covered in our last video connect to this same fault system, That video is linked below. And if you want to understand how earthquake early warning systems give people those critical extra seconds, that's coming up next. Subscribe if you'd like to see it.